Thank you very much. Thank you for inviting me. I'd like to present the system I've been working on. Working title is QPEL, Quantum Programmable Effect Language. It's a system of logic in which we can write both quantum programs and properties, or predicates, or effects, sometimes called fuzzy predicates, of quantum systems. And that we can reason about these programs, make prove properties such as their correctness. There are several different mathematical structures used to give semantics to quantum programs. Hilbert spaces, C-star algebras, W-star algebras, more exotic things, AW-star algebras, von Neumann algebras. But many of them fit this pattern. We have a category, the category of Hilbert spaces, whose objects are intended to represent the quantum systems, and whose arrows represent the quantum programs, or the actions of the quantum programs. We have a set of probabilities. When we have a system and a pair and a predicate, we want to talk about the probability that that predicate holds for that system. And these probabilities always form a structure known as an effect algebra. We have the predicates themselves, the effects, and in each of these cases they form a structure called the effect module over that effect algebra. And the states of each quantum system form a convex set over that effect algebra. And these three categories fit together in this pattern. We have an adjunction between the effect modules and the convex sets. The category, in this case Hilbert spaces, of systems and programs sits underneath both. Let's call this sort of structure state and effect triangle. This is a sort of structure that has been studied in Bart Jakob's recent work quite extensively. So the system, QPEL, is the logic of state and effect triangles. It's a set of all judgments that are true in any triangle of this form. I'll give it syntax and semantics. Syntax, the rules of deduction, and then how the judgments are interpreted in any state and effect triangle. The QPEL itself, as a framework intended for any state and effect triangle, we'll need to add something to it. We want to talk about the particularities of quantum programs. We'll need to add something to QPEL if we want to talk about qubits. I'll give one example of how that can be done, the rules, and give one example of reasoning about a program in this setup. The example of superdense coding. So, the syntax, QPEL. Before we start, I'll talk more about the structures involved in the state and effect triangle. It said the probabilities form an effect algebra. The definition, an effect algebra is a structure where you have an operation, partial operation, or the sum of two effects is not always defined. We have an operation of orthocomplement, which gives we think in terms of Hilbert spaces, the orthocomplement of an effect is the states that are orthogonal, the states in that effect. Satisfy these rules. This notation, by this notation, we have two expressions involving partial operations. I mean, E is defined if and only if F is defined, in which case the values are equal. So our disjunction is commutative and associative wherever it is defined. We have 0, which is a unit for disjunction. And the orthocomplement is a unique element, so the disjoining x with x inner with x bottom gives you one top element. Canonical example is a set of all real numbers between 0 and 1, which disjunction is addition as long as that keeps you under 1. The orthocomplement is 1 minus x. We can also have classical logic, which go just 0 and 1. And in fact, any Boolean algebra is an effect algebra, with disjunction defined if and only if the two elements are disjoint. It is their conjunction 0. Given this effect algebra, the effects themselves form an effect monoid over that effect algebra. Similar to the structure, similar to the way I beg your... I confused monoid and module. No, I'm right. Thank you. Given that, here we can, given an effect algebra, we just extend the structure to an effect monoid. An effect monoid is an effect algebra with a multiplication defined on it, which behaves roughly similar to conjunction. This notation I use to mean if E is defined then F is defined, in which case the values are equal. So so the multiplication distributes over the disjunction when defined. Top element, truth, is a unit for the multiplication, and multiplication is associative. All our examples turn out to be effect monoids. Given an effect monoid, which we use to represent the set of probabilities, the effects themselves, the quantum predicates, form an effect module over this effect monoid, similar to the definition of a module over a ring. An effect module is a set, is an effect algebra, together with an operation, together an operation of scaling. This should be thought of as given a probability and an effect, form, so if this is a probability 1/2, form the effect totals 1/2 of the time. So multiplication is distributes over the disjunction when both are defined, and it is an action on the effect algebra. For example, the effects over the Hilbert space form an effect module over the set of real numbers from 0 to 1. The effects, positive elements below 1, in the C-star algebra form an effect module, again over the real numbers from 0 to 1. And the states of a system form a convex set over the same effect monoid. For a convex set, it consists of a set of states, and an operation so that given a test, given an n test, that is, given a set of n predicates that are all disjoint and which sum to 1, so roughly exactly one of these must be true of any state, we can form this state, which we think of as a superposition of x1 and xn, given these n scalars, such that certain covariance equations hold, which we won't list down here. The density matrices over a Hilbert space form a convex set over the real numbers from 0 to 1, and the positive unital maps from A to the complex numbers for any C-star algebra form a convex set over the real numbers from 0 to 1. So here's a structure that we want to give the logic for. We have an adjunction between convex sets and effect modules. Given any convex set, the set of all affine functions from that set to E form an effect module. Given any effect module, the set of all effect module homomorphisms from that module to E form a convex set. These two functors together form an adjunction, and the settings in which we want to interpret quantum programs all form this structure, a state and effect triangle, where we pick an effect monoid for our set of probabilities, we pick a symmetric monoidal category with binary coproducts for our classical control for when we split into two cases, that distribute over the tensor such that the tensor unit is terminal. We demand a functor which, given any quantum system, gives us the effect module of all predicates or effects over that quantum system, and we demand that that preserve finite coproducts and a terminal object. We demand a functor which, given any quantum system, will give us a convex set of all the states, the mixed states, we should think of these as, will give us a convex set of all the states of that system, and we demand that that be a symmetric monoidal functor. We also demand these things. This is the setup I'm using at the moment. Given a set of effects that sum to 1, the disjoint, we have an arrow in here which will give us the program that performs this measurement. Given a set of n effects going up to 1, we can take a system and perform the measurement with n outcomes, which decides which of these effects is true of that system. We ask for the program, which we're given a state, returns take the case n equals 2, this would take any effect and return a bit. It's true if we measure if the outcome of that effect if the system is in that effect, and false if it's in the orthoconfident. We demand the n-fold version of that. And we demand natural transformations from P to this functor, from S to this functor, which behave well together. These give us the interpretation of when a predicate is true of a system. This, think of as given a predicate, gives you a functor which, given a state, will perform the measurement of that predicate on that state. So, given a predicate and a state, this returns the probability that we will get that predicate will be true of that state. The probability that we will get true when we measure that predicate on that state. And beta should be alpha with the two arguments reversed. Given a state and a predicate, returns the probability that that predicate is true on that state. We want to give a syntax for this structure. A syntax that will pick out all and only the judgments that are true in every structure of this form. Examples again, finite dimensional Hilbert spaces with unitary maps and C-star algebras with positive unital maps form a state and effect triangle using 0, 1 as the probabilities. Here's our syntax. For the types, we have these are the types that are guaranteed to exist in any of our categories V. We have the tensor product, the tensor unit, and the co-product. Our terms in this syntax will be intended to represent quantum programs, and we have a second category of expressions with effects intended to represent the predicates on the quantum states. 4 different judgment forms that we can build out of these. We have that a program takes input of type gamma and returns an output of type A. The 2 different programs form the same calculation, the same quantum operation from gamma to A. That phi is a well-formed effect on the quantum system denoted by gamma. And the derivation relation. That in any state, this quantum system, phi will have lower probability than psi. Phi is, as quantum operations, phi is less than or equal to psi. This will perform the result of this. We can read intuitively as given phi, we can derive psi in this logic. It's a linear type system, so we do not, in particular, we do not have a contraction rule. We cannot use a variable twice. This, of course, corresponds to the no cloning theorem. It says that we can't use a state of a quantum system twice. Once it's used, the information in it has been destroyed. Here are some of the rules. I'll start with effects. The rules for forming effects say that if say pretty much nothing more than that the effects form an effect algebra. We have 0, we have the complement of each effect. Given a scalar, a probability, and the scalars are represented by the effects in the empty context, given a scalar and an effect, we can perform the multiplication of the effect monoid. We'll want the derivation relation to be reflexive, transitive, or the complement to be antimonoidal, and so many other rules, which from this point on are pretty much just writing down the definition of an effect module. The one rule that's a little different is how we represent the partiality of the disjunction. Phi or psi should be defined if and only if phi is orthogonal to psi. And it turns out that phi is orthogonal to psi if and only if phi is below the orthocomplement of psi in the order. So we can put this into the logic by allowing these 4 judgment forms to depend on each other in an unexpected way. We can only form the proposition, the effect, phi or psi, if we have already derived the judgment from phi. You can deduce the orthocomplement of psi. The structural rules for the typing system. We don't have contraction, but we can swap variables about as we like. If x is type A, then x is type A. I'll show you the rules for the tensor product. Given a state of A and a state of B, we can put it together into a state, the tensor product of A and B. Given the state of the tensor product of A and B, we can extract its two components and use them. Similar, the rules for the tensor unit and the coproduct are also exactly what you'd expect, going through like a linear type theory. Measurement. We want to be able to represent we want to be able to put a measurement step into any of our quantum programs. And the rules for measurement look like this. First, we can only measure if we have a set of effects that sum up to 1. Everything is below 1, so to say sum up to 1 is the same as saying 1 is less than or equal to the sum of these effects. If we have n effects that are orthogonal, so their sum is 1, and n programs, we can form this program which performs this measurement on a state of gamma, and then derives into n, and then splits into n cases depending on which outcome was obtained. In the case that phi 1 is true, we perform m1. So in the case phi n is true, we perform mn. This must satisfy these rules. We can commute for p any permutation of 1 up to n. We can commute the measurements. Measuring over 0, if the case turns out to be measuring over 0, we can just drop it. Measuring over 1, and performing m in that case, is the same as just performing m. And in the case of scalars, in the case where we're in the empty context, measuring over phi plus psi, performing m, is the same as saying if phi is true, perform m, if psi is true, perform m. I will add one more rule. This is also a congruence. We can replace m with anything equal to m, and we can replace an effect with any effect that is equal to it, and by equal, I mean phi and psi are derivable from each other in the logic. To give semantics, given a state and effect triangle, we give an object for each type, an object for each context, an arrow for each quantum program, an element in the effect module of all predicates for each effect, an element in the effect monoid for each scalar. For example, to interpret the measurement program, we take the n effects, take the measurement arrow, which reflects those n effects back into the category of programs. Given that, we will get n times the tensor unit, tensor product with delta, which is isomorphic to n times to the coproduct of n copies of delta. And we can then perform whichever of m1 and mn is appropriate, according to which case we're in. It's straightforward to show that any derivable judgment is true in any state of effect triangle. We can also prove a completeness theorem. Any judgment that's true in any state of effect triangle is derivable. By true, I mean if m and n have the same interpreted as the same arrow, then the judgment m equals n is derivable. And if phi is interpreted as an effect that's below psi in the order given by the effect module, then we can derive phi is less than or equal to psi. Proof, we construct a term model. We construct a state and effect triangle out of the syntax of the system itself. The category V is the category whose objects are the types of QPEL, the arrows are the programs, the terms of QPEL, quotiented by n equals n, by derivability of n equals n. The effects are the effects of QPEL, quotiented by phi equals psi, if we can derive both phi is below psi and psi is below phi. That lets you interpret any state and effect triangle. I haven't really done anything quantum yet. The idea of the state and effect triangle is more general than quantum computation. In order to do something quantum, we're going to have to represent qubits somehow, and the things we can do with qubits. And it's pretty modular. All this goes through however we add qubits, or the other particularities of quantum computing to it. So there should be several different ways of doing it. Here's one way of doing it, which are based on the rules of the measurement calculus, which can be interpreted in finite-dimensional Hilbert spaces, C stars and W stars, but as I say, not in an arbitrary statement-effect triangle, because the idea of a statement-effect triangle is more general. We give ourselves a type of qubits. We give ourselves a state. Let's give ourselves 0, 1, we can then get it by applying z to 0. We give ourselves these operations, which measurement calculus shows a universal. We can apply Pauli operations x or z for any qubit, and measurement in what's called in the measurement calculus entanglement. This is control z. Given 2 qubits s and t, we can perform control z on s and t. From those operations, we can get any unitary operation. We also give ourselves an effect that we can measure over. Given a qubit, we can measure it in the basis plus alpha and its complement, where alpha is 0 plus e to the I alpha times 1. So it's a qubit with phase alpha. The equations for these qubits. I took these equations from the measurement calculus. If we entangle x, s, and z, that's the same as performing x tensor z afterwards, and a similar rule for e, s, and xt. If we perform control z on z, s, and t, that's the same as performing z tensor I afterwards. Measuring xt, basis alpha, is the same as measuring in the basis with phase minus alpha. Measuring zt and alpha is the same as measuring in alpha minus pi. 2 rules which aren't in the measurement calculus, but I think should be. X and Z are self-inverse. Let's say how this behaves with the effect anomaly structure. The complement measuring in alpha is measuring in minus alpha. And X and Z commute up to global phase. Maybe you want to quotient out the category V by global phase, but no, but certainly in any statement effect triangle, we want it to be that measuring XZT gives you the same outcome as measuring ZXT. Let's do the example, superdense coding in this setup and prove that it's correct. Here's a setup for superdense coding. Alice prepares 2 entangled qubits in the Bell state, sends 1 to Bob. Later on, she wishes to send two classical bits to Bob. She wishes to send an integer between 1 and 4 to Bob. She looks at the integer, performs an operation on her qubit, depending which integer she wishes to send, sends a second qubit to Bob. Bob measures both qubits in the basis B1, or x tensor I times B1, z tensor I times B1, xz tensor I times B1. From that, he learns with certainty the value of I, but if Eve intercepts the second qubit, there's no way she can extract the value of I from that 1 qubit alone. To prove this correct, give ourselves some shorthand first. We can write the Hadamard operation in this language. To perform Hadamard on T, you would entangle T with 1, and then measure the left-hand side of what you get out, and perform X according to what you get. We can write controlled not in this syntax as well. You entangle perform control not on S and T, entangle S with HT, and then perform H on the second thing. We'll give ourselves some axioms. I hope sooner or later to be able to derive these from more elementary axioms, but for now this is what you need to prove superdense coding correct. We give ourselves axioms that say that Hadamard is self-inverse and that controlled not is self-inverse. Perform control not on ST, perform control not on what you get back to ST. We'll also give ourselves axioms that say that these 4 states form a basis for qubit tensor qubits. Again, it'd be nice if we could derive that from rules for qubit and tensor alone. But for now, we say everything must be in one of these states, and these states are orthogonal. If you measure EI, if you perform the measurement, does Q equal EI on the state EI, you get 1 with certainty. If you perform it on any of the other states, you get 0, and XZ and ZX commute even when they're inside the tensor product. This is what we need to prove superdense coding correct. Here's superdense coding written out in this syntax. Here's the Bell state. Form controlled knot on Hadamard of 1 and 1. Alice looks at Z, performs one of these 4 operations on the Bell state, sends it to Bob. Bob measures it according to the basis B1, B2, B3, B4, and returns 1, 2, 3, 4. And here's B1, B2, B3, B4 written out in these cases. And by the effect Q equals BI, I mean C naught Q, Hadamard times I performed on C naught of Q is equal to EI. What we really want to say is Q is equal to Hadamard inverse, C naught inverse on Hadamard inverse of EI. We can say that by saying Hadamard C naught of Q is equal to EI. Again, we can derive these rules. Everything is here. These 4 states form a basis for qubit tensor qubit. And if you're in a subspace, you'll get 1. If you're in an orthogonal subspace, you'll get 0. Here's the calculation. Let's do it for 3. Perform this calculation for each of 1, 2, 3, and 4. Form superdense coding with 3. This is what you get. The Bell state, form Z tensor I, and measure. This flips measuring of Zx and Y is the same. This is just replacing TA with Zx and Y. Measuring, let me write this as shorthand. Measuring of Zx and Y. Let me form this as shorthand. Then let's expand the definition of the state equals BI. This is C naught of Zx and Y, Hadamard of that equals EI. What do we do here? Measuring in Zx and Y is the same as measuring, and then performing Z and then measuring is the same as measuring and then performing Z. That was one of the rules from the measurement calculus. From the fact that C naught is self-inverse, this reduces to this. We're measuring Hadamard of Z, Hadamard of 1 and 1 against each of the basis vectors E1, E2, E3, E4. Expand out the definition of Hadamard and use the rules of the measurement calculus. You find that Z of Hadamard is equal to Hadamard of X. Hadamard of X of 1 is Hadamard of 0. Use our axiom that says Hadamard is self-inverse, and we're measuring 0, 1, according to whether it's 1, 1, 1, 0, 0, 1, or 0, 0. Write that out. This is the measurement we're performing. Use the fact that each of these is 0, and this is the effect 1, the top effect. According to our axioms, we get this. Use the rule that says measuring 0 can be discarded, and then use the rule that says measuring 1 and performing the program M is the same as performing M. We get STC of 3, gives output 3. Do that for each of 1, 2, 3, and 4, and use our rules for code product. We can prove performing superdense coding on any of the integers from 1 to 4 will return that same integer. I beg your pardon, I've gone a little over time. So I'll talk very briefly about some work with a similar aim. There is LQP, the logical quantum programs, which again is attempting to give a system where we can reason about quantum programs. The biggest difference is that their language for quantum programs, their term language, is deliberately an under-specification language. It just says there's some behaviors of the programs, rather than being full programming language, the way I'm trying to do. And likewise, Panangaden and Ying try to give a Floyd Hall logic for quantum programs, but for them, the effects are given directly as operators on quantum states. They give a syntax for programs, whereas I'm trying to give a syntax for both programs and effects. So, we have a sound and complete system for state and effect triangles, and I've shown one way to specialize that to a state and effect triangle with a type that behaves like qubits. Qubits. It should be a system in which we can reason about quantum programs. Here's some ideas that I'd like to add to this system for the future. Thank you.
Quick questions?
So probably I missed
listed, but where in your verification example did you use this logical implication?
The step where it's used, the main step where it's used is here. Using this rule, it says if two effects can be done, if two effects apply each other, then measuring on one effect is the same as measuring on another. So here we use the fact that that the effect 0, the false effect, can be derived from 0, 1 equals 1, 1, and vice versa.
I see. Thanks.
Any further questions? Answer speaker again.